Welcome to the second video in the third chapter of the curriculum. József, what will we talk about next?
Mostly about how we have progressed from machine code to high-level programming languages and how we can process it in an embedded environment. The need to make programming easier appeared in the 1950s, and the assembly language was the solution. The assembly language replaces opcodes or groups of opcodes with the same logical effect and binary codes in registers with mnemonics. Mnemonics are short identifiers of a few characters, labels, and often abbreviations, which essentially function as instruction names. For example, add indicates addition. The machine code is generated from the mnemonics by a software program, the assembler, also referred to as assembly compiler.
The assembly language has also made it possible to use relative addresses for jumps or substitute labels for relative addresses. It was also the first time when it is possible to organize programs into multiple files and to structure the code using subroutines.
A subroutine is a part of a program that, like a C function, is a separate block expected to be executed several times, making the program more transparent and shorter because of subroutines. Relative address resolution and concatenation of machine code from each source file is done by a program called a linker. Linking will be discussed in more detail shortly. So you can see that the conversion of the assembly code into machine code, that is the compiling, is a two-step process. And these two steps are very often present in the build process of higher level languages. So at some point in the build process, an assembly code is generated.
Programming languages are often grouped according to the extent to which they hide the specifics of the hardware being used from the programmer, or in other words, how closely the logic of executing machine code approximates the usual human way of thinking. This is known as the level of abstraction. The more closely a language follows the human way of thinking, the higher the level of the abstraction.
In all architectures, there are so-called control transfer instructions. This means that an instruction is not followed by the next instruction in the program memory during execution, but by another instruction elsewhere. Such instructions are called jumps. In this case, the memory address from which execution continues must be stored as an operand of the machine code. However, when writing a program, it is not yet known which instruction will be placed at which memory address, since it is possible, for example, to insert a few instructions into a previously written section before compiling. In assembly, it's allowed to replace specific memory addresses in the program with labels, as in the case of the next jump instruction. The jump, main plus 0, 32, this describes the sequential continuous execution of the program to continue 32 hexes offset from the address indicated by the main label. The labels will not have their real memory address, they are in fact the address of the first instruction following them. Replacing such labels with memory addresses is done by the linker. The input to the linker is the output of the assembler, that is a file or files in the case of multiple source files, in which the mnemonics have been replaced by machine code, but the memory addresses have yet to be determined.
Alright, but how can you use a high-level programming language to program a microcontroller?
It's a good question, but before we answer it, let's consider why it's worth programming in a high-level language. As we have seen, there are different instruction set architectures, so the machine codes that can be executed on different microcontrollers to perform the same task can differ significantly. Since in practice, different types of microcontrollers may be suitable for different projects, writing programs in a low-level language will require too much time spent mapping out the available instructions and learning their syntax before each project. To avoid this, The need arose early in the development of computing to be able to write a program and have it converted into machine code by an automatism without going into details about the instruction architecture. One such solution, which is still very popular in embedded development, is the C programming language.
We have seen the syntax and basic language elements in the 10th chapter of the Crystal Clear Electronics 1 curriculum. Now let's take a closer look at what the whole compiling process looks like.
The build process can be broken down into 4 major steps, as shown in the figure. These are the pre-compiling, converting to assembly code, this is the compiling itself, and running the assembler, and finally linking. The C programming language is a standard, so several vendors and software communities can make their own compilers, which many did in the 1990s.
There are subtle differences between the various compilers. Unfortunately, not all of them have fully implemented the whole standard, and there are extra features that are not included in the standard and only work on a specific compiler.
The remainder of this chapter covers the GCC compiler maintained by the GNU project. Its modified version is used by the Cube IDE development environment, which we will use to build our project and will be covered in the remaining chapters of the curriculum. GCC is short for GNU Compiler Collection, and it's free, open source software in line with the GNU project's goal. GNU is short for GNUs, not Unix, as the project originally set out to create a free operating system.
Let's get back to compilation for a moment and take a look at the 4 steps to see what functions they perform.
Alright, the first one is the precompiler, which has the role of performing initial text processing. This involves replacing certain special character sequences with other characters, deleting comments from the source code, converting end-of-line characters to uniform format, as different operating systems use different characters for this purpose. In addition, the precompiler concatenates statements into a single line that is conveniently split into several lines in the source code, but logically forms a single unit. In addition, it makes further transformations to the source file based on so-called directives. Directives are not part of the C language, they are merely instructions to the precompiler, and once the precompiler has executed the instructions, the directives are removed from the preprocessed code.
Instructions for the C precompiler are case-sensitive, like language keywords and lines starting with a hashtag. For example, hashtag include.
The simplest working directive is define, also called macro. It allows you to replace any string, called an identifier, with another string within the source code. However, this operation does not replace the C language keywords in the code. The most obvious use is to define constants. A generic example is shown in this code snippet. Since the preprocessor does the resolving of the identifiers, the lines do not end with semicolons when the directives are given, since the example above already looks like this to the compiler. It's important to see that the precompiler is merely performing character substitution. There is no check that the correct type of data is being inserted during the precompiling, and insertions are only made if there are exact matches.
The fact that identifiers are resolved by the precompiler also means that they can be used in places where they must be evaluated at compile time without running the program, just based on the code written.
Yes, for example, defining arrays. In this example, we could not even replace the length identifier with a constant variable, because in C language, somewhat confusingly, the const modifier is actually a read-only variable, but at compile time, it has no value yet. The situation is complicated by the fact that the C++ language already treats variables with a const modifier as real constants, i.e. they can be evaluated at compile time. GCC supports both languages, so depending on usage, this may not be the case. Although C++ compilers are increasingly available in the embedded world, it's good practice to have C files containing C code and not C++.
The define directive also differs from the use of const variables in that space must be allocated for variables in data memory and its value must be copied there at runtime, whereas the values specified using define are stored in program memory. Thus, if you need to converse data memory, which is usually much less available, you can use define. However, in this case, we lose the advantages of the const type variables, that is more readable code, and verifiable type conversions.
The define directive can also be used with parameters, in which case the parameters are listed between parentheses, separated by commas after the identifier, so that the function-like operation can be implemented without actually calling a function in the compiled code. For example, in the following code snippet, the value of parameter changes depending on the value of the variable x, indicated by the x in parentheses.
Why is it important whether a function call is actually made? Or rather, what happens when a function is called?
The location of a program in memory is basically continuous, so consecutive instructions are located at consecutive memory addresses. However, in the case of a function call, a jump occurs, so execution can continue with an instruction at essentially any address, and upon return, a jump to the original location of the code execution is made. In this case, it's expected that the value of the local variables of the calling function will be preserved, and it may also be necessary to restore the values of certain registers to maintain correct operation. The compiler generates machine code that saves these to a special part of the memory, called the stack, before calling the function and restores the values of the required registers and local variables on return.
Then this must be a large memory area.
Not necessarily, you just have to use it wisely. If you have a lot of nested function calls in your program, it can occur that the space needed for them in the memory is run short. This phenomenon is called stack overflow. For embedded projects, this can lead to hard-to-detect errors, as variables used elsewhere are overwritten with seemingly random values. In an embedded environment, memory is usually scarce, so if you need to conserve memory, but still want to write the most organized code that is possible, it's worth replacing shorter functions with macros.
The downside of saving memory is that the same code appears in multiple places in the program, which can result in longer machine code.
So, in the end, it's easy to find that saving data memory comes at the expense of program memory, similar to storing constants. In both cases, the best solution can be found by considering the specifics of the development. Such decisions are an important part of engineering. If we only want to use the given identifier in a part of a source file, we can use the #undef directive to override the #define you specified earlier. When using #undef, you only need to specify the macro name. If anything else is in the line, it will cause an error.
The include directive has already been introduced in Chapter 10 of the Crystal Clear Electronics 1 curriculum. This instructs the precompiler to copy and paste the given file as a parameter into the current source or header file. In the example in the previously mentioned chapter, the standard input-output header file was copied.
A source file can contain any number of include directives, And it is also possible that the pasted file contains additional include directives, in which case the precompiler will of course perform those insertions as well. Although the precompiler can include any file, in practice, the include directive is only used to include header files, and everyone is encouraged to always use it to include header files only, as unconventional use may be misleading to others.
The concept of a function prototype has already been mentioned in Crystal Clear Electronics 1, Chapter 10. A prototype is also called a function declaration, which consists of the name of the function, its return value, and the types of the function parameters, and optionally, the names of the parameters.
This may be done in conjunction with the description of the function's trunk. This is called an implicit declaration, but it is not mandatory to do both together. The specification of the function's trunk is called the definition of the function. This is the part where we describe the instructions that the function will execute. In C, this is enclosed in braces.
The fact that the function declaration or prototype can be separated from the function definition is important because it allows for efficient modularization.
Without the separation of the declaration, it would be impossible to organize our programs into several compiling units, since the precompiler would have to copy all the functions used, together with the function body, into the file containing the main function, while this way it is enough to include the prototypes, since it already contains the necessary amount of information.
Therefore, the header files are where the prototypes and constants are placed. Each header file also includes source code, which contains the definitions, or in other words, the implementations of the prototypes.
Further directives of the C precompiler are related to conditional compiling, with the possibility to create blocks of codes that are only translated if a given logical condition is met.
The fact that the header file can contain additional include directives can lead to the problem of multiple definitions. This can occur if you want to use a common function in several source files.
For example, a circuit takes temperature measurements and also reads in the position of a potentiometer. Suppose that the results of both types of measurements need to be averaged, but you don't want to write the code that implements the averaging more than once, so you put it in a separate source file. We also put the temperature measurement and the potentiometer handling in separate files to make the project more organized. Thus, temperature.h and potentiometer.h files are copied into the main file by the preprocessor, so average.h is included twice. Therefore, the preprocessor will also copy the average.h file twice into the main file, leading to multiple definitions of the averages function, which will cause a compiling error.
To avoid multiple definitions, conditional compiling directives are used. This is most easily done using #ifandef, #define, and #endif, as shown in the example program.
Header files are started with a #ifandef directive, which checks whether the identifier specified here has been previously defined. If so, the part up to the #endif directive is ignored by the precompiler. The identifier will be defined between #ifandef and #endif, so this block will be inserted once only. The translation process can also be broken down into further steps. GCC is a compiler collection that supports many languages other than C, such as C++, Fortran, or Go, as well as many instruction set architectures. The compiler also performs optimization, which would have been wasteful to write separately for all supported programming languages and instruction set architectures combined. Accordingly, the compiler produces additional intermediate code during the compiling process, independent of the language and the instruction set architecture on which it can perform the optimization.
We haven't finished with the C compilation yet, but we will end this video here. Stay tuned for the next part. Bye!
Bye!